Ever wondered how ChatGPT actually works under the hood? How does it generate text that sounds so human? In this video, we're going to build a large language model from absolute scratch. No libraries, no shortcuts. Just pure understanding. By the end, you'll know exactly how LLMs think. Let's dive in. Section 1. What is an LLM? At its core, a large language model is a next token prediction machine. Given some text, it predicts the most likely next word. It's trained on trillions of tokens from the internet. Books, Wikipedia, code, conversations. It doesn't truly understand language, it recognizes patterns at an incredible scale. And that's enough to seem intelligent. Section 2. Tokenization. Before an LLM can process text, it needs to convert it into numbers. This is tokenization. The standard approach is byte pair encoding or BPE. Common words like the become a single token. Rare words get split into pieces. GPT-4 has about 100,000 tokens in its vocabulary. Let's build a simple character-level tokenizer first to understand the concept. Section 3. Embeddings. Token IDs are just arbitrary numbers. We need to give them meaning. An embedding table maps each token to a dense vector, typically 768 dimensions. During training, the model learns that similar words should have similar vectors. King and queen end up close together. We also add position embeddings so the model knows word order. Section 4. Self-attention. This is the core invention that makes transformers work. Every token looks at every other token and asks, how relevant are you to me? We project each token into three vectors, query, key, and value. The dot product of query and key gives the attention score. We scale it, apply a causal mask so tokens can't see the future, then softmax to get weights. Section 5. The transformer block. We combine self-attention with a feed-forward network. Multi-head attention runs multiple attention operations in parallel, each learning different patterns. The feed-forward network is a simple two-layer MLP. We add layer normalization and residual connections to keep training stable. GPT-3 stacks 96 of these blocks. More blocks, more capacity, better language understanding. Section 6. Training. The model predicts the next token, we compare it with the actual next token using cross-entropy laws, and then adjust all the weights using gradient descent. We use the Atom W optimizer with learning rate warm-up. Training happens in batches of thousands of sequences. For a real LLM, this process runs for weeks on thousands of GPUs. But the concept is exactly the same. Section 7. Text generation. Once trained, we generate text by feeding a prompt and sampling from the predicted probability distribution. Greedy decoding always picks the top choice but is boring and repetitive. Temperature controls randomness. Top K limits sampling to the top K candidates. Top P, or nucleus sampling, is even smarter. It samples from the smallest set of tokens that covers a cumulative probability. This is how ChatGPT generates diverse responses. Section 8. Scaling laws. The amazing thing about transformers is that performance scales predictably with more data and more parameters. The Chinchilla paper showed the optimal ratio is about 20 tokens per parameter. Our model has about 1 million parameters. GPT-4 has an estimated 1.8 trillion. Same architecture, just massively bigger. Plus they add RLHF reinforcement learning from human feedback to make the model helpful and follow instructions. And that's it. You now understand how large language models work from the ground up. Tokenization, embeddings, self-attention, transformer blocks, training, and generation. The same architecture powers ChatGPT, Claude, and every frontier model. Drop a comment if this clicked for you. Like and subscribe for more deep dive AI tutorials. See you in the next